Good morning, everybody.
Good morning, sir.
Today, today we are okay. So far, what is the story? The story is we had what we call the strong form or the differential equation. Okay, and that differential equation also comes with some boundary conditions. So this is we are talking about the boundary value problems. These problems have some exact solutions. However, those solutions could be difficult to find out sometimes. Yeah. But actually, I would say that most of the times, because the engineering problem is complex. Yeah. So in that case, what we do, we want to find out some approximate solution. So in order to find out the approximate solutions, there are various methods, and we use, so far we have learned Galerkin method and the Rees method. Both of them has some alternative formulation. So instead of the strong form, we have, in Galerkin case, we have the weak formulation, and for Rees method we have minimum potential energy formulation, or you also called variational form. Yeah. Okay. And accordingly we proceed. In all of these, our requirement is, if you see here, in Galerkin method, you have this kind of things coming into picture. So it will be like some dw over dx, du over dx, and there will be some constant. So far we know that EA could be EA here, or could be KA in case of heat transfer, or will be like dA in case of diffusion, right? So it will vary, but in all cases, so U will also be T in case of heat transfer, or U can be concentration C in case of diffusion, right? So this will vary, otherwise the form remains the same. So this is in case of Galerkin. In case of Rees method, we have some sort of this half EA, and it will be, so you have a stress time strain, so this will be du over dx square dx type form. Yeah. So here in case of Rees method, so what you see here is a square of U. So that means this puts some restriction on U, right? So we have studied that these and these are basically the same form. Basically, we also get the same kind of solutions, right? So, and we also proved that actually this is the variation of this only, right? So if you minimize this one, this comes to something like this one. So basically, we have some U has some property, and what we call is U has to be, yeah, should belong to what we call H1, right? So we write H1, that really means this is kinematically admissible. Yeah. So here there are a few things. First of all, this is it has to be integrated, right? And then this is a square of it. Yeah. And this is the, we have this also. So derivative of U has to be should be such a way that it can be integrated. So meaning that our requirement is du over dx square dx has to be less than infinity, right? So this is one requirement. This will happen in what case? This will be possible only when u has to belong to what we call it C0. Okay, C0 is smoothness we are talking about. So has to belong to C0. What is the meaning of C0? C0 is like your x, we have u, and if it is varies like this, then what happens? Du over dx will vary. So this will be something like here, this will be here, this will be here, for example, right? So this can still be integrated, right? A square of it, still you can integrate it, because du over dx is from here to here, it is this much. So we can identify this is x1, this is x2, this is x3. So we have x1, here we have x2, here we have x3. But still you can square it and you can integrate it. So as long as you can do it, you can take that u. So really that tells you that piecewise. So what it tells you that piecewise polynomial is one of the solutions, right? You can, solution will be some which is something a piecewise polynomial is also a possibility, because polynomial between two values will have a smooth, this is a smooth curve. If it's a line, this becomes a C0. This C0 actually really tells you that this is continuity we are talking about, right? So in continuity means if you differentiate it, then you get a discontinuous line, right? So this is when you say C1, that really means you can, this is even if you differentiate, then even then that will be, so let us say if you have kind of like this, yeah. So this or maybe we say quadratic, let us say this is a quadratic equation, right? So if you differentiate it, then you get this kind of thing, yeah. So this is quadratic, this is a line. Just hold on guys, just sorry guys, some urgent call from director's office. Okay, so here we are talking about the continuity, and this we also discussed earlier. So we have some nomenclature for the continuity. So if we have discontinuous or something like we go like this one, this kind of curve. So this is a certain jump. So what we see here is a jump. If you have jump, this kind of curve, we say a smoothness of this kind of curve is C minus 1. When there is a kink, so there could be some kink, right? So kink, something like this, right? So if you have kinks, yeah, but continuous, we call this smoothness is C naught. And if there is no kink, nothing like this one, yeah, this is a smooth. So it could be, if you integrate this one, for example, if you integrate this, then this will be something like goes up, goes down, like this, you know. So you have this, you integrate this, you get this one, you can integrate this one, this, you get this one, right? So this will be what you call it is C1. So C1 means if you differentiate it, you will get kinks, right? As C0 is, if you differentiate, you will get discontinuous. So this is what it is. So requirement is, as long as you have this kind, means there may be some kinks, but continuous. This is the one that can be a solution. So solution could be, you have different x's, x1, x2, x3. Within that, it can change. Yeah. Within that, there may be a kink, may have a kink. Yeah. But it is continuous. But it is continuous. Okay. Fine. When we say U belongs to H1, this one really means that this is kinematically admissible. Yeah. And that really means that U has to belong to, first of all, U has to belong to C0. That's one thing, because if it is not, then you cannot calculate, you cannot do the calculations. So you know that it has to be piecewise curve, which is continuous. If it's not there, it will not be able to calculate, do calculations. So this is a requirement. Apart from that, this also you has to satisfy essential boundary condition. So it has got two properties, right? Your trial function has two properties. One, it has to be continuous like this, and other is you has to satisfy the essential boundary condition. Yes, Sobhana.
Sir, could you please explain, sir, why U belongs to C0, sir? Please.
I explained already.
Okay, sir.
I explained already, no? So which part you are not comfortable?
Sir, I cannot understand why U belongs to C0, because there is C1 and C minus also. That's why I am asking.
No, that I explained already, man. So you give attention to what I say, okay?
Okay, sir. I'm sorry, sir.
Okay, so see, wherever you are, like whether you are working from the weak formulation, where you will get this kind of form, right? So you will have some constant or some few things which will be a function of x, and then you have dw over dx, then you have du over dx, right? Dx, you will have like this over the domain. This should exist or should be finite, right? So du over dx should exist, right? And should be finite as well. Otherwise you cannot do this, right? If you look from the Rees method, then also you have some phi x, and then you have du over dx square dx. Yeah.
Yes, sir.
Here also you see that this has to be finite. This also tells you that this is also, you know, like du over derivative is a square integrable. So you also call it is a square integrable. That really means that du over dx has to be finite to begin with, right? Otherwise, you cannot square integrate it. Right? So a square integrable means what? That really means that if you have, let us say, if you have this kind of du over dx, if you have du over dx, which is something like this one, then you call it du over dx is a square integrable. That really means you can integrate du over dx, a square of it dx over the domain, right? So it is just the area, right? A square integrable means you can find out the area here, right? So this is what the area will be, right? Right? So this requirement you want to get. And that really means what? If that is the case, then du over dx belongs to C minus 1. That really means U belongs to C naught.
Okay, sir. Now clear, sir. Now, thank you, sir. Thank you so much, sir.
Okay. It can also be not necessarily, this is the minimum requirement. It can be you can choose such a way, this is C1 as well, C2 as well, but not C minus. U cannot be, U does not belong to C minus. Otherwise, you will have difficulty calculating du over dx and you cannot solve it. Yeah, got it?
Yes, sir. Clear, sir. Thank you.
Okay. Now, given this background, we now delve into finite element method. So you had already Galerkin method, you had the Rees method. Now this finite element method is just extension, the further refinement of those methods. You will still use those variational form or minimum potential energy form or the weak form. However, your trial function we will change. It will have all the properties that we have seen, and trial function we know that it can admit piecewise polynomial as solution. So what happens in finite element method? You work on piecewise polynomial as solution. And how we do it? So let us say you have same problem we are talking about. Now, of course, we know that area can change. So area is a function of x. E can also change, is a function of x. There may be a body force, as we know, and then there may be a boundary force as well, or traction we call it. And in that case, we can say that solution is something like, if you are plotting u as a function of x, we can assume that our solution is piecewise polynomial like this. Okay, so x equal to 0 doesn't matter. It should start with 0. So let me mix here, bring it here. So x equal to 0 is 0. Then there is somewhere, let's call it x equal to x1, this is x equal to x2, this is x equal to x3. Yeah. And then accordingly, we have whatever the value. We say that we want a solution which looks like this, which is a piecewise line or piecewise polynomial. I can fit it, right? This is a still a solution, and we can do it because if you say, because to begin with, I am imposing already u is a u belongs to C naught, because if you du over dx will be horizontal lines and it will be not be connected, right? There will be a jump and hence this will belong to C minus, but still it is derivative is a square integrable, right? We can integrate it. So basically this will be as a solution. And what is the advantage? Basically what we are doing is we are making three elements, element number 1, element number 2, element number 3, and we are putting here 4 nodes. This becomes element number 1, this element number 2, this element number 3, and for all these, for this element the solution is varying linearly, for this element solution is varying linearly, for this element also solution is varying linearly. And since they are connected here, they should share the same u from both the sides. Hence, we are imposing that to begin with. Only thing is, du over dx will be different in this, du over dx will be different in this, because if you see, that really tells you that the internal force, right? If you cut here and the reaction force, if you see here, the value will be different, here it will be value different, it will be different, and it can be different given the body force it has. But the idea is this, that now if you do that, we can increase the number of elements, and in that case our solution can be, so many elements, so it can now capture all kinds of solution if you take high number of elements, right? You can follow a curve as well if you take sufficiently large number of elements. That you can see later on, but this gives you a background from where we can work on, right? So let's start with a problem where it has only one element, right? So the very simple one, it has E and A which are constant, fixed at one end, and it has a force applied here at x equal to L. In that case, how to solve that problem? How to, whatever we thought about, how do we do it? The concept it has is as follows. Your only thing is you will start with the weak formulation or minimum potential energy formulation. There's no problem, you can do the same thing. However, only thing is your trial function is equal to, you are saying ux will be equal to, you have here, so let's equal it node number 1, equal node number 2. And within that, we are already telling that ux is linear. Ux is linear. So how can we make linear? We can write this way. We can write, let us say you have u1 is the displacement here, u2 is displacement there, and then we want to interpolate. How will you interpolate? You can say like this. You can say this is 1 minus x over L times u1 plus x over L times u2. You see, you can formulate like this one. This is also a line. This is also a line. How it or we can write is equal to, let's call it n1x u1 plus n2x u2. And how will n1 x will look like? This is x. Our n1 will look like this. So this is 0, this is x equal to L, this is 1. And this is how so this one is n2x, this one is n1x. Yeah, so there are two polynomials, both are linear, but n1 is varying from 1 to 0, n2 is varying from 0 to 1. Yeah, and then we are writing like this one. So you can see that the value, whatever we wrote here, if you put x equal to 0, then what happens? You put x equal to 0 here. So you can check it. u0 is equal to, you put here, 1 minus 0 over L times u1. So this becomes 0, 1 times c. So becomes u1 plus, and you put 0 here, and then this is gone. So you get 0 is equal to, so u0 equal to u1. So satisfied. Similarly, if you put ul is equal to, now put L here, this becomes 1, 1 minus 1 is 0, so this term is gone, so you get 0 plus, you put x equal to L here, and then it becomes 1, so it becomes u2, so u2 is equal to u2. And you know that this is linear, so if two values, if the boundaries are matching, if u0 equal to u1, ul equal to u2, between that it has to vary linearly only. There's no other way. So this one, n1x is a polynomial, n2x another polynomial. This n1x, you call it a shape function. Both are called shape functions or interpolation functions. Yeah. Okay. Good thing is you are writing in terms of now the displacements. That's a good thing. Yeah. You can write is I equal to 1 to 2. Yeah. N I X U I. Right. Okay. Now we can now go back to the Galadkin method. We just formulated this way. Now we will use the Galadkin method. Yeah. So from the weak formulation, so you know that in this equation remains the same. We have the strong form d over dx ea d over dx, right? Plus bx equal to 0. Here in this case, no body force, so 0 we are saying, Ea equal to constant, right? So our equation is simply Ea, doesn't matter, we don't need to specify. Then we have boundary conditions. It is fixed at one end. So u0 equal to 0. So u0 equal to 0. Yeah. And that really means we will see that. So u0 equal to 0. And then we have force. So Ea du over dx at x equal to L is equal to F0. That's what we have. Now, we can find out the weak formulation. So we start with W, d over dx, Ea du over dx, 0 to L, d terms is not there, that's fine, is equal to 0 simply. or we get W EA du over dx L0, right, minus 0 to L 0 to L and EA dw over dx du over dx. Fine. Okay. And this is equal to 0. Here we put the value. So we know that this value, if you put this F naught, so this becomes W at L multiplied by F naught minus W at 0 times EA du over dx at x equal to 0. So we know that this value becomes 0. Okay. And then we have minus we have this value. So we have 0 to L EA dw over dx du over dx equal to 0, or simply we get EA dw over dx du over dx 0 to L is equal to F naught WL. Now we will put U as a function of this. U is, we are writing as Ux equal to N1 x U1 plus N2 x U2. Now, what do we have U1? U1 is nothing but, for us, U1 is equal to U x equal to 0 is equal to 0. We have that. So we can put that 0 here, or simply we get is equal to N2 x U2, right? Okay. Now we have U2 term here. U1 we know already. Yeah, so we have U2 term here in this case. U as a function of U2, we are getting U2. Earlier we used to get the, what did we get? We get the coefficient. But here, displacement itself as a coefficient we are doing. So that's the new thing we are doing, right? Similarly, Wx can also have, you can write it as Nix Wi. Similarly, you can do, like if there is U1, U2, U3, you also have W1, W2, W3 at those x. Yeah, and since W0 equal to 0, you can write it here Wx equal to N2x multiplied by W2, right? So this is what the W you get.
Excuse me, sir.
Yeah.
Sir, at boundary point, the sum of shape function values are 1. Can it be equal at intermediate points?
I did not get you. Say again.
At boundary points, N1 plus N2 is equal to 1.
Yeah, it will be 1.
Can
Yes.
it be equal at intermediate points?
Yeah, why not? There will be half in the middle somewhere, right?
Yes.
Here both will be half in the middle at x equal to half, x equal to L over 2, both N1 and N2 will be half each. We will look at the property of the shape function and all later on.
Okay.
Right now, we want to connect it with what you know already and the motivation why we are doing it. So we will come back to later on where we will not refer to the Galerkin method or the Rees method. We will just go ahead with, we will just have our own, the method that typically used for finite element. So
Thank
So
you, sir.
that we'll do later on. But right now we are connecting it with what we learned so far. This gives you continuity. This is also historical background. It is this is along the history in the past how it moved from those Galerkin method to finite element method what we are seeing right now. So this I want to show the continuous progression how so that you also understand. It's good to actually do the way it developed over the time. So this is what I'm doing. So I'm not delving directly into the in the usual methods that you use. Okay, so this wx you got like this one. So this is all the familiar thing. What we changed here, just the trial function we have changed. Trial function we are not writing as c1x plus c2 x square term like not like that. We are using the displacements as the coefficient, so that's a smart thing to do, and I tell you why. You will come back later on, maybe not today, but next week we will learn more. But here also we can see something. So you have ux as n2x u2, right? So du over dx, you get dn2 over dx, then u2 d over dx, you know n2 is nothing but x over l u2, so you get u2 over l. Then you have dw over dx equal to d n2 over dx w2, and similarly you get w2 over l. So looking at this first term, we will have ea multiplied du over dx will be du over l, sorry, u2 over l multiplied by w2 over l dx 0 to l, this is the left hand side, is equal to ea. Now w2 and all of them are constant, right? We use them as a constant. So ea u2 w2 over l square multiplied by l, right? So all constant out, and then integration of this is simply l, so you have that, and which is equal to ea u2 w2 over l.
Sir,
Yeah.
sir, these values of u and w are for x is equals to 0.
No,
So we found that u at x
no,
is
no.
equals to
See here. This is x equal to 0, x equal to L. At x equal to 0, you have u1, and x equal to L, you have u2, right? Then this is w1 here. Value of w is w1 and w2, right? But you know that u1 equal to 0 and w1 also equal to 0 because of the requirement that w has to be 0 where u is given, and
okay.
u1 is comes from the boundary condition itself. Yeah, so this is 1 means node number 1, 2 means node number 2.
Sir, we took u of x is equals to n1x into u1 plus n2x into u2. Then we did u at x is equals to 0 is equals to 0. And then we are using the same thing for the further calculations. So
Right.
these values of u of x is for x is equals to 0 values only.
How, man? See, this is ux n1x u1 plus n2 x u2, and you know u1 equal to 0, right? Means u at node 1 is equal to 0 because you have fixed already. So ux becomes n2x times u2.
Yes, sir, that's what I'm saying, that these values are for node 1 only.
What do you mean by node 1 only? Ux is for the whole thing, no?
No, sir, ux, not ux. I'm saying that what we are finding right now, LHS, in the LHS part,
Hmm.
right now. in the LHS part, what
No,
we are finding.
this is for the whole element, man. It's not like for node 1 only. So we don't call it like that.
So
U
might
is
be
a,
he means to say that we have put the boundary condition for the LHS, that is at x equal to 0, u1 is equal to 0.
okay. No, I'm not getting what you're saying. So, of course, boundary condition, the essential boundary condition only we'll put, no?
Yes, sir. That is fine.
Hmm.
Okay, that is the mention.
Only the essential boundary condition only we put, no? Other boundary condition is natural boundary condition. So we will not apply that, right?
Yes. Yes, sir. Yes, sir.
Got it?
Yes, sir.
Yeah. So this is the essential boundary condition. So hence we have like this only. You can see the expression also, no? This will be x over L u2. See, continuously is increasing. We are assuming u to be linear, and hence if you have x equal to 0, it will be 0. If x equal to L, it will be u2. Right? U2, we
Yes,
have to find out what that is. Okay. Now we have right hand side is equal to. So what is on the right hand side? We have this F naught times W at L. So we have F naught at W at, and W at L is what? W2, right? W at L is W2. X equal to L is node number 2. So W2. So left hand side equal to right hand side. And what do we get? From here, we see here EA U2 W2 by L. EA W2 U2 by L is equal to F naught W2. Okay, again W2 arbitrary. We can impose that W2 is not equal to 0. Yeah, it's up to you. So hence we have EA U2 over L is equal to F naught, and hence U2 equal to F naught L over EA. So this is, you directly you got the nodal displacement. Yeah, earlier you found the C1, C2, those coefficient, and then you put value of X to find out U. Here, directly you get the nodal displacement. Nothing to do. And then you have Ux equal to what? N to X U2, and hence you have X over L multiplied by F naught L over EA is equal to Fx over EA. So you found out the solution this way. You got it? Got it, guys? Another advantage from here is you also can find out the strain. So strain equal to du over dx will be d over dx, and you have, what do you have? You have n to x. In this case, you have n to x times u2. So you have dn2 over dx times u2, and n2 is nothing but x over L multiplied by u2. So you get 1 over L times u2, and u2 is F naught L over EA. So F naught L over EA. So you get F naught over EA as a strain. Yeah, and a stress equal to E times epsilon, and here you get E times F naught over EA is equal to F naught over A. And you know that force by area is stress. just to show the simple things. Yeah, and yeah, you will see that automatically it follows. Yeah, okay. Still, we have not got K U over F type of thing, stiffness, how the stiffness comes into picture. We have to connect it now. Whatever we have done so far, chapter 2, we looked at Ku equal to F. It's not that we just do there and we forget it. No. There is a meaning to it. We will come back. Later on, we looked at the differential equation. We tried to solve differently. We looked at how to formulate the problem. We look at in order to find out the approximate solution, what to do. We change the form itself. Then we try to change the trial function itself. So this is where we are. Trial function itself we have changed. Yeah. Now we'll do something else. In trial function we are writing, we will assume, although we know that either this or that can be given, right? Either you give displacement or force, but we can do some general purpose formulation in which we can give this essential boundary condition, this also, at the same time we can also give a natural boundary condition as well, just to make it general purpose, and so that we can accordingly we can formulate the general purpose some formulation, and there we will see that automatically it follows that we get some form Ku equal to F, so that we integrate whatever we learned so far. In chapter 2, we Ku equal to F. Now we have equations. We will get the same form from the differential equation now. From the differential equation. And for that, we have to give the essential boundary condition. We assume that both are given to begin with, and from there we find out the values, so we will find out in this form basically. So just to give you a hint, we will automatically find this will be E over L 1 minus 1 minus 1 1, and we will get U1 U2 is equal to F1 F2. So next class we will prove that we can get this from a differential equation. Which equation? From the weak formulation you can get. That means what I mean to say is this equation d over dx dA du over dx, yeah, that is equal to 0 will lead to this. We prove that this also means this. This we have done earlier, but we did it what we call it the direct method. Here we are not doing the direct method. We will use the proper mathematics to prove this or get this one. Once you get this one, you know how to do it. In chapter 2, you already studied how to now assemble a stiffness matrix and how to apply the programming and do it. So once we do it, then everything is connected. You will know that why we studied this one first, why didn't studied this one, why we studied Rees method, why we studied minimum production energy method, why we used U as unknown as coefficients to be found out in the equation, so that we can get this kind of thing. Yeah. Any question, guys?
Sir, I have a question, sir.
Yeah.
Sir, here the shape function that we have taken are linear functions, and in the solution we end up getting the u in some function of x. So if we take the shape function of some higher order term, so will it be like u is function of x square or x cube in that case?
Yeah. We will see that later on. In that case, what happens? Like if you want a shape function u x to be quadratic, let us say, right? Quadratic. Then in that case, we will see later on though, but still I give you a hint that in that case you will write ux equal to, you will have to take a 3-noded x u I equal to 1, 2, 3. You have to take 3-noded element. We'll come back to later on, okay? But I'll just give you a hint that in that case you have to formulate an element which has 3 nodes, yeah, and within that you have you will have 3 kinds of shape functions, and the shape function is going to move something like this. The first will be going like this, so the second, this one will go like this, and the third one will go something like this. It may be like this. Understand? Something like this. Okay. So we will see that. No, sorry. It should not be like this. It will be 0. Okay. So we have exactly at half here. So we have x equal to 0. This x equal to half. L over 2. X equal to L. So 1, 0 here will be 0. Second will go here from 1 here, it will be 0 here, and then third will go 1 here, 0 at these two. So we get something like that. So you have n1 here, this is n2, and this is n3, and you have u1 here, u2 here, and u3 here. And these are quadratic equation. These are all quadratic equation, and we have to find out how it looks like, this equations are. This is what we will do. We'll do later on.
So, like in the same problem, if we take higher higher order, so we'll get some different solution, or number of nodes if we increase.
The different solution. Yeah. Number of nodes decides the order of the polynomial. Yeah.
Sir, so thus we can say that this 3-noded element will give better approximation compared to this previous one.
Yes, that really means that. Yeah. True.
Okay, sir. Thank you, sir.
Okay, sir.
Any other question, guys? This, all those things we will do. Okay, so this just a precursor. We are heading towards that, so before we have to make enough background so you understand what is going on. Okay, so we want to give the slow slope so that smoothly we get into all those. So we will do it. Okay, any other question?
Excuse me, sir.
Yeah.
It's out of my curiosity, sir. In practicality, what could be the distance between two noded? If you take any structure, what could be the distance? Will be the in between two nodes?
Distance.
Either it can be or order of nanometers, centimeter, like that. What could be the order of?
No, it depends on the problem, man. You cannot tell like that. You cannot tell like it's a mm or it is micrometer or nanometer. It's not like, it all depends on the problem. Yeah.
Okay, sir.
Depends on the problem, the scale of the problem. If the whole thing, if the whole structure is nanostructure, so of course you have to take a small, even below the nano scale. If the lot of things are in meters, so of course your elements will be few centimeters one, right? So yeah, all depends on the problem.
Thank
yeah,
you,
Rohit.
Sir, one thing I'm just curious about, like here the functions which we have taken, that is n1, n2, and this n3. As we can say this that at x equal to 0, n1 has some value. So can we, sir, these functions are like predefined. Like can we just interchange from n1 to n3, and still we get the same answer, or can we take
No.
some other functions?
They have some properties, so we will see that. Property
means,
you
sir-
see that, see, n1 is multiplies to u1, right?
Yes,
So
sir.
n1 should be 1 at node 1, then it should be 0 at node 2, should be 0 at node 3. Similarly, n2 multiplies to u2, hence u2 has to be 1 at node 2, has to 0 at node 1, has to 0 at node 3.
Yes, sir. At a particular node, its value should be 1. Yes, sir.
Right. So it has definite form, so you cannot interchange.
Yes, yes. Okay, sir. Thanks.
Yeah. Okay, guys, any other question? Okay, guys, I have uploaded the homework, so please do it. The last day is like Sunday, I think. Okay, just before the midnight. Okay, so please finish it. Give time to it. Okay, so this is for your own good, because quiz or midterm exams will be similar patterns. Okay, so get used to it. Okay. Okay, guys, that is all. Thank you very much. We'll see you next week. Have a nice weekend.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.